In this video you will learn about drift velocity, which is the speed of charge carriers in a conductor caused by material parameters and by the electric field, which for example is produced by a battery which is connected to a copper cable. We will look at the flow velocity of electrons, which is surprisingly low, and we will also discuss how drift speed, drift velocity can be used to later derive the concepts of current and also voltage, which is among the topics of the next videos to come. My name is Andreas from The Fearless Engineer, and here we go. In this video we want to find out with which speed electrons actually move through a certain material, for example a copper cable. And in order to understand this, we first need to understand what electron mobility is. We need to discuss the velocity of charge carriers in an electric field, and if we understand both things here, we can easily arrive at a computational result of the speed of electrons in a copper cable. And by using the equation at which we arrive by the end of this video, we can then in the videos to come arrive at a very sound definition of electric current and also later voltage, which can easily be explained by using this concept of drift velocity. If you bring a cloud of electrons under the influence of an electric field, you will find that this cloud starts to move along in a certain direction, and the speed with which they move along these particles is called drift velocity, Vd. And this drift velocity, it does not describe the velocity of an individual electron in this cloud, but rather it's the average velocity of the entire cloud against the field direction. And the drift velocity Vd is given by the following formula. It's called Vd equals the electron mobility times the electric field. It's a very simple form which we can use to compute the drift velocity, and it depends on two factors. It depends on the material through which the electrons propagate, for example copper or aluminum or any other material, and then it's the influence, the strength, the magnitude of the electric field which permeates this material. And these two parameters combined, they make up the speed with which this cloud of electrons moves along. Let's make an example here. Let's find out how fast electrons can move along in a copper cable. And in order to arrive at a result by using the equation which we have seen on the last slide, we can look up the electron mobility of copper, which is 4.3 times 10 to the power of -3 square meters divided by voltage times second. We have not yet defined voltage, so ignore this unit here for just a moment longer. And we also have an electric field which permeates the copper cable, and this field, for our example, is defined at a strength of 1 volts per meter. So if we combine the two, we cancel out the volt and we cancel out 1 meter, and the drift velocity here in this case is approximately 4.3 millimeters per second. So millimeter is the unit here, which is really slow. If you take an individual electron, it will move at a higher speed, but if you look at the whole electron cloud, you will find that it moves along with a very slow speed of only about half a centimeter per second. And in order to give you an understanding of the magnitude of this electric field here, which is 1 volt per meter, you might want to consider a power line, an overhead power line, and if you stand directly below this power line, you will encounter an electric field of about 1000 volts per meter. So it's really a small electric field which permeates this copper cable. Now let's try to answer a question here. If the drift speed really is so low at about half a centimeter per second, why does the light, when you press the switch on your wall, come on immediately after you press the switch? Because this implies that the electrons move at light speed, for example, or something close to light speed. And the answer is, even if a single electron moves along very slowly at about half a centimeter per second, the electric field, which propagates through the cable, which permeates the cable, affects all the electrons simultaneously. So once you press the switch and close the circuit, the field propagates the copper cable, and the electron which is directly in front of the light bulb also starts to move along at the same time at which the electron directly behind the switch which you just pressed started to move. So even though the electron directly behind the switch or behind the power source takes a very long time to get to the light bulb, the electrons directly in front of the light bulb will start to flow through the bulb immediately, which causes the bulb to light up just after you pressed the switch. And now, after you know what drift velocity is, you have all the necessary basics in place to really understand the term current flow, which we discuss in the next video to come. For now, that's all. I hope you enjoyed the video. If you have any questions, please do not hesitate to drop me a question down below in the comments. I wish you a nice day. See you next time here on The Fearless Engineer.